name is Megan Tracy, and I'm a graduate student at the University of Wisconsin-Madison. My fellow graduate students and I study thin films as part of our research, and we want to share some of the fun aspects of our work with you. We made this video to show you some experiments with thin films that you can try at home. Hopefully these activities will be fun and also show you some cool aspects of thin films. Thin films are really important in our world. Semiconductor manufacturing for electronics and cell phone displays are two examples of the applications of thin films that are important in our everyday lives. First, we wanted to come up with a way that all of you can make thin films in your own home. I'm going to show you how to make some with nail polish. This activity is designed to be fun and colorful, and is almost the same as a nail polish technique called water marbling. This technique is also similar to the way patterned paint can be applied to hard surfaces on objects like electric guitars or bike helmets. In the following activities, we will figure out just how thin films like these are. Nail polish is a polymer mixed with a solvent. Polymer is a long stringy molecule. Plastics are one common application for polymers. The polymer in most nail polish is called nitrocellulose. Nitrocellulose is a solid, which means that in order to be able to apply the nail polish, the nitrocellulose needs to be dissolved in a liquid called a solvent. Often ethyl acetate or butyl acetate is used as a solvent, and in the jar, nail polish is actually mostly solvent and only about 20% polymer, with added dye or pigment to give it the desired color. If these details don't interest you, that's fine. We just want you to know what materials we're working with. To do this at home, you will need a stick that can get dirty, a cup or bowl that you don't mind getting nail polish on, a couple different colors of nail polish, some paper towels, some plastic bags, scissors, and you'll probably want to have nail polish remover on hand as well in case of any spills or accidents. First, you're going to want to cut up the plastic bags to make squares of flat plastic about the size of your hand. Maybe a bit bigger or smaller depending on the size of the bowl or cup you're using. You should make as many squares as you want to make films. Then fill up your cup or bowl with room temperature water and unscrew all of the nail polish bottles that you plan to use for your pattern, leaving the brushes in the bottles. When you're ready, pull out the first brush and let a drop of polish fall into the center of your cup. You may need more polish. Then, quickly put a drop of another color into the middle of that drop as it spreads out. Repeat this until you have at least 4 layers, or as many as you want to make your pattern. Once you have your film, get out your stick and start making a pattern. You can do this however you want, either by dragging lines all the way across the film, or by pulling individual layers in or outward. So in, or out. Do this quickly but carefully, and make sure to wipe off your stick between drags or the film will start to break and bunch up. As soon as you're done with your pattern, you'll pick up the film using the plastic square. So place the plastic square carefully over the center of your pattern and push it down with your fingers, running over the entire film to make sure it sticks to the plastic. Be sure to get all the edges. Give it a couple of extra seconds, then carefully pull up the plastic. And set your pattern aside to dry. Before you make another pattern, you're going to want to skim the surface of the water with a paper towel to pick up any remnants of the film so that it doesn't get in the way of the next drop of polish. Now we're going to show you a couple of techniques to try to figure out just how thin films like these are.
Hi, I'm Ben Casting, and today I'm going to show you how to make thin films of clear nail polish. Later on, we'll even find out how to measure the thickness of these films. Start by finding a bowl with a flat bottom about a few inches wide. Then, take some black construction paper or cardstock and cut it down to size so it fits nicely against the bottom of the bowl. I like to give mine a little handle to make things easier later. Place the paper in the container and fill it with the minimum amount of water needed to completely cover the paper. Make sure the paper stays flat against the bottom of the bowl. Now, get the clear nail polish and add 1 drop to the center of the paper and wait about 1 minute. Like Megan said, Nail polish is a polymer dispersed in a solvent. The polymer does not mix with the water, so it spreads out into a thin film on the water's surface. As the solvent evaporates, a solid polymer film is left behind. We have to wait to give the film enough time to solidify before transferring it to the paper. We use the handle we made earlier to slowly pull the paper up through the nail polish film, and then set the paper aside to let it dry. Here's one I made earlier. As you can see, our black paper is now extremely colorful. Stay tuned to find out how this is possible.
Hi, my name is Xin. For the next activity, I'm going to estimate the average thickness of the film that Ben just made. To do this, we'll be using the volume of a drop of nail polish. So, let's measure it.
First, I let one drop fall on the glass plate. Then, I measure its height and diameter. We can see that the height of its highest point is about 2 mm, and the diameter of this drop is 5 mm.
A key for this measurement is that don't let the nail polish lay too long in the air, or much of the solvent would have evaporated before your measurement.
Now, let's do the calculation. First, we approximate the average height of the drop to be 1 mm. Then we calculate its bottom area and then volume. Considering polymers make up 20% of the nail polish, the volume of the polymer film would be 4 mm3. Then, using the area of Ben's film, we get its thickness, 2 micrometer. That's pretty thin, 30 times thinner than the human hair.
Hi, Ben again. Now that Enron has given us an estimate of the film thickness, let's use a few things from around the house to get a real measurement of the film thickness. The lights in the room contain all colors, which is why the film appears as a rainbow. Let's see what happens if we only shine one color on the film using an LED. Now we see alternating light and dark stripes on the film. This is caused by light interfering with itself, and we can use this to get a real measurement of the film's thickness. Some of the light reflects off the top of the film, and some enters the film to reflect off the bottom. These beams interfere with each other to create the alternating light and dark stripes or fringes. The wavelength of the red light here is 614 nanometers in air, and shortens to 409 nanometers in the film because of the difference of refractive index. The bright spots occur when an integer number of wavelengths fit within the film. When illuminated and observed from directly above, the film's thickness can be calculated as the wavelength divided by 2. Based on Enron's measurement of the film thickness and the wavelength of the LED, we can calculate the thickness of the film at each of the bright fringes. There is some ambiguity in this measurement, and we only really determined the range of film thickness. Next, let's find out how to unambiguously determine the absolute thickness of the film.
Hi, my name is Marie Fiore, and I'm another graduate student at the University of Wisconsin-Madison. In my research work, I make a lot of really thin films, and I need to know precisely how thin they are. To do that, I use an instrument called an ellipsometer. This ellipsometer uses the interference principle that Ben just told you about, and it can measure film thickness really precisely. So let's see how it works. So today, I'll be measuring a thin film of nail polish, just like the one Ben made earlier. This film was made on silicone though, instead of black paper. That just makes the measurement much easier to do than with the paper. So I'm measuring with the ellipsometer now, and here's how this works. So light comes in from a source, and this is white light, so it's a mixture of all different wavelengths, and then it reflects off of the sample. When it reflects off the sample changes the light. Kind of like how water makes straws look different when they're under the water, and it makes them look kind of bent. That's also why polarized sunglasses cut out the reflections of the sun off of the water. We measure the light over here after it reflects off of the sample. So when we collect the reflected light, we can measure the interference effects, and it's recorded onto this computer. From that interference, we can determine the absolute thickness of the film. Unlike Ben's measurement with the LED, we are using white light. Ben only had one wavelength of light, but we have many. This graph shows the thickness of the film at different points across the sample. The different colors explain how thick the film is at each point we measured. The red areas in the lower left show where the film is about 500 nanometers thick. The purple area at the upper right shows where the film is the thickest, about 1,000 nanometers. Even at its thickest, this film is still much thinner than a human hair.
Hi, my name is Yejong Lee, and I'm a graduate student at UW Medicine. I want to take 1 minute to talk about two different ways that color can be generated: light absorption and interference. The color from light absorption is from pigment or dyes by selective absorption and reflection of specific wavelengths, whereas the color from interference is from structures, such as the shape or the orientation of the material. You have seen them both in this video. Here are some other examples of color that result from light absorption: the colors in fabric and in your hair. Can you think of examples where color is generated by interference? What about soap bubbles? Some really dramatic colors in the insect world result from interference too. Here are some pictures of beetles. Look at their iridescent colors. That's from the light interference.
Hi, my name is Mark Ediger, and I'm a chemistry professor at the University of Wisconsin-Madison. We hope that you will enjoy trying some of the thin film activities that we've shown in this video. You may wonder, what do we all do when we aren't making videos? The graduate students that you have just met are pursuing research projects to understand how to make new materials with the best possible properties. We study how to improve the properties of polymer films, how to make them tougher so they don't break when they're stretched or bent. We also study how to improve the very thin films used in cell phone displays. Our research is supported by grants from the U.S. Department of Energy and the U.S. National Science Foundation. We thank you, the taxpayers, for investing in fundamental research that can influence the future.